So this is the second lesson in chapter 15. To review from lesson 1, what we did in lesson 1 was we really practiced sketching curves using those critical points. So we're going to be looking at the first and second derivative again today, but in terms of the second derivative, we're going to actually be using it to help us determine whether or not a point that we find from the first derivative is a max or min. So this eliminates the need to use the increasing and decreasing number line that we've used in the past. If we're just looking for the max and the min, this is a little faster way than doing that number line. So here is how the second derivative test works. So we have two rules. The first being that when we have f prime of q equal to 0 and f double prime of q is greater than 0, we have a minimum, and that minimum exists at x equals q. And a maximum exists at x equals q when f prime of q equals 0 and f double prime of q is less than 0. So what we're noticing here is a minimum. We know that we can find the x-coordinate of the minimum by setting f prime of q equal to 0 and solving for those values. Okay, so that's the same in both of these. What tells us if it's a max or min is what happens when we take those values and we plug them into the f double prime equation. When it's greater than 0, it's a minimum. When it's less than 0, it's a maximum. So let's go ahead and kind of explore this a little more. You may be wondering what happens if f double prime of q equals 0. Well, if f double prime of q equals 0, it doesn't mean that that point isn't a maximum or minimum. It just means that we can't use the second derivative test to find that point. And what we need to do is we need to go back and look at the number line for increasing in for the points on the graph that are increasing and decreasing using the first derivative. So whenever we have, f double prime of q and our result equals 0, we have to use the first derivative and the increasing and decreasing number line to see if there's a max or a min. Okay, so let's start with this function f of x equals 3x to the fourth plus 1. So I'm just going to go ahead and take both the first and second derivative. So I end up with 12x cubed. And f double prime of x is equal to 36x squared. So let's go ahead and find the x-coordinate of our max and min by setting 12x cubed equal to a gradient of 0. So when we do this, we end up with x equals 0. Okay, so we have potentially a max or minimum at x equals 0. We're going to take this value now for the second derivative test and plug it into the second derivative. So we're going to say f double prime of 0 equals 36 times 0 squared. Well, this is our case where f double prime of 0 yields 0. So we can't tell using the second derivative test if 0 is a maximum or a minimum or neither. So what we're going to do is we're going to go back to the first derivative and we're going to do a number line like we did during lesson 1 to see if the graph is increasing and then changing to decreasing, or decreasing and then changing to increasing. We're basically looking for a change in direction to confirm that this point x equals 0 is a maximum or minimum. So I'm going to go ahead and substitute negative 1 in for x and f prime of x, and I end up with negative 12. So all the values less than 0 are negative. When I substitute 1 in and cube it, I get 1 times 12, which is positive. So I have a change in direction, which means my graph looks something like this. It goes decreasing, decreasing, hits 0, which is the minimum, the x-coordinate of 0, and then it starts increasing in the other direction. So we need to find the y-coordinate, so that brings us back to our original equation, f of x. So I'm going to go ahead and substitute 0 in for x everywhere in this equation, and I know that you all can do this in your head. I'm just trying to be thorough. Okay, so f of 0 equals 1, so our minimum is 0, 1. Okay, so let's practice another one. So this one's a little trickier. I'm going to go ahead and rewrite f of x such that everything's in the numerator. So I'm going to rewrite this using the definition of negative exponents as 2x to the negative fourth minus 1 times x to the negative 1, or x to the negative 1. And now I'm going to go ahead and differentiate. So f prime of x equals negative 8x to the negative fifth plus, right, because negative times negative 1 is 1, x to the negative 2 power. Okay, now I'm going to go ahead and find the second derivative. So f double prime of x is equal to 40 x to the negative sixth minus 2x to the negative third. Okay, so now what we need to do is we need to factor out f prime of x so we can solve for x. So I'm going to go ahead, and what I notice is both of these equations have x to the negative 2 in common. Okay, so I'm going to pull that out. I'm going to have negative 8 here, x to the negative 3. So I'm just dividing negative 8x to the power of negative 5 divided by x to the power of negative 2. It's the quotient rule of exponents, so we then subtract the exponents, so I'm getting x to the negative third power plus 1. Okay, so if I want to go ahead and set these equal to 0, I'm going to do it by each part of our equation. So we know that, whoa, wait, hold on for a second. X to the negative 2, I don't think I can divide by 0, because this is another way of writing this is 0 equals 1 over x. Is there anything we can ever put in the denominator that will result in an answer of 0? Hopefully you know that that is not possible. So even though we kind of ended up trying to solve for 0, it's not impossible. We know that the domain of this function, x can never equal 0. It can equal other things, but it can never be 0. There's an asymptote there. Okay, so let's do this part here. So 0 equals negative 8x to the negative third plus 1. I'm going to subtract 1 from both sides. And now I'm going to divide by negative 8. So 1/8 equals x to the negative third. Running out of room here. So x equals positive 2. Okay. Okay, that's an equal sign. Okay, so this is our point, or our x-coordinate. So I'm going to now take this x equals 2 and plug it into the second derivative. Really crooked line there. Okay, so in the second derivative, f double prime of 2 equals 40 times 2 to the negative sixth minus 2 times 2 to the negative third. Okay, if I were to just put this straight away in my calculator, I would get f double prime of 2 equals positive 3/8. Okay, so what this tells me is since f of 2 is greater than 0, I have a minimum at 2. So to find where that minimum is, I'm going to go ahead and I'm going to plug 2 into my original equation. Let me get rid of some of the stuff on the screen. I'm going to plug 2 into my original equation. So 2 divided by 2 to the fourth minus 1 divided by 2 equals f of 2. Okay, so that's 2 over 16 minus 8 over 16. I'm just writing this with a common denominator, equals f of 2, which equals, I had a leftover there from when I next went to grab it and put it in the garbage. So 2 minus 8 is negative 6 over 16 equals f of 2, which equals negative 3 over 8. So our minimum is 2, negative 3/8. Okay, So that is how you use the second derivative test to find out whether something is a minimum or a maximum.